There we go. Okay. Equilibrium is in recognition that by far most reactions do not go 100%. But what happens is that they go part way, and then, so you have a forward reaction, and it goes part way, and a reverse reaction starts to occur. Okay? Now, please understand that it doesn't mean it gets halfway and both are feeding back and forth at the same rate. It's not that way at all. In some cases, the reaction goes very far to products, but there's still some products that are re-entering the reactant stage. It's back and forth. So at the point where the forward and reverse reactions are equal, that's equilibrium. Okay? So let's start chatting a bit here. So overall chapter, talk about dynamic equilibrium to begin with. There's two types, dynamic and static. So there's most of the writing is done for you. I've given you a condensed version so we don't have to do much writing. Equilibrium, I'm going to try to put definitions in orange. So equilibrium is when the forward and reverse reaction rates are equal. So here we have our good old friend, the energy diagram. And yeah, it carries over. And so we have, for example, where is this pen? We have two reactants, and there shall remain anonymous. Only the colors know what they are. And so at the activation energy, we have bonds broken, and quasi-bonds formed. And then as it goes forward, bonds reform like so. So forward reaction, and reverse reaction. For the reverse reaction, the energy of activation is greater than for the forward reaction. Okay? We good? Now it turns out that in order for equilibrium to occur, and this goes right off the question we did from the Green Book. In order for equilibrium to exist, the reaction must be in a closed system. So that's the first piece of information, the first clue that they start asking a question about equilibrium, and it's not in a closed situation. They're tricking you, okay? And it must be closed. Why? Why must it be closed? Yes, sir.
Because if gas leaves the system, somehow the same gas must get re-into the system in order for the equilibrium?
Yeah, because the products are the reactants for the reverse reaction. So if you lose those items, they cannot reform to come into equilibrium. Okay. One of the things that's quite interesting, you guys, have you guys ever had like full-on like aspirin, or have you guys Tylenol, ibuprofen, all these new drugs? You ever? Yeah. It's interesting. When I was a kid, I think all we had was aspirin. Just good old Bayer aspirin. Thing with aspirin is really interesting. If you have a bottle of aspirin and leave it in the cabinet for very long, You open it up and it smells like vinegar. Have you ever noticed that? Nobody, okay, I've noticed that in the past. I thought it went bad. Well, in a way it did. Because this is what, going back to organic chemistry, you see here, this is acetyl salicylic acid, which is ASA or aspirin. Okay? So you can see that you have a benzene ring here. We have a carboxyl group on here, or the acid group on here. And we have this acetyl group on here. Okay? So the difference between the acid and the acetyl is that you have a methyl group instead of an OH here. Okay? So if you look across the page, here, salicylic acid looks a lot like this, except it's instead of the OH off here, it has this acetic acid, CH3COOH. So that's acetic acid. So in the manufacture of aspirin, they actually combine these two. But if it's left long enough, this will go into it's a reversible reaction. So some of the ASA will become just salicylic acid and acetic acid. It loses its potency if it goes back in this other direction. Okay? Another interesting one is dinitrogen tetroxide. Dinitrogen tetroxide, N2O4, is a colorless gas. And if you add heat to it, you'll get 2NO2, which is a brown gas. Okay? Oh, delta means heat. That's a short form for heat. Okay? Are we good? Everybody's happy? I'm just trying to find. Okay, so in Hebden, says, read the following observations and answer the questions. 2 sealed glass tubes containing a mixture of red-brown gas, NO2, and a colorless gas, N2O4, are observed. So it's a mixture of two gases in the same thing. So it's a mixture of NO2 and N2O4 in the same glass tube. The color is an identical medium brown to each, oh, there's two of them, I'm sorry. The color is an identical medium brown to each tube, and there is no visible change in the color of the contents as time passes. One tube is placed in a beaker of boiling water for a minute. The content of the tube becomes much darker red, brown in color. Upon first placing the tube in the hot water, the color gets continually darker, but after a few seconds, the color stops changing. Okay? You got the scenario now? Okay. Page over. The second tube is placed in a beaker containing dry ice at minus 78 degrees Celsius. The color quickly disappears and the contents of the tube remain colorless. The hot and cold tubes are taken out of their beakers, placed side by side, and allowed to come to room temperature. The tubes have an identical medium brown color when they are both at room temperature. A, the gases are involved in a reversible reaction, as we indicated. And I think as I put on the other one, just to remind ourselves, I'm going to put actually this way, because we're adding heat to here, okay? What evidence exists that the forward and reverse rates are equal at room temperature? Sir?
That when you put one heat with the other, you put them both at room temperature, they both reverse the same color?
And? That's right, but what else happened? They remained at that color as long as it was sitting at room temperature. Okay? Can temperature change affect an equilibrium reaction? And how do you know this? Can they?
Yeah.
Yes. See above. Yeah, because the reality is that even at any temperature, this is happening. Some of the N2O4 is going to NO2, and some of the NO2 is going this way. The difference is that if you increase the heat here, if you increase the heat, it shifts it to this side. More NO2 is produced. If you cool it, it shifts it back to this side. Yeah.
Will there ever be a point when none of the N2O4 goes to NO2?
Well, if in a situation where it's at minus 78 degrees Celsius, yeah. Yeah, it's stopped. It won't. Well, he's saying none. None that's detectable. You won't see it in color, but there probably are still some molecules that are.
Maybe 1% or whatever?
Oh, probably less than that. Okay? The same is true when we talk about solubilities. We say something is insoluble. That's a lie. There may be almost close to zero items being dissolved and recrystallized, but there are some. Okay? What evidence shows that the forward and reverse reactions rate are equal at, what did it say there? 100 degrees Celsius. Well, you can see my little writing there, because there's no further color change. If the temperature were raised above 100 degrees Celsius, what we'd expect to happen to the color, and you can see my little notation, you expect it to darken, because you're pushing it even farther over. See, at 100 degrees Celsius, even though it's gone dark brown, it's not 100% there. It's still a mixture of the two gases. Okay? It's just how far in each direction are they. Okay? That's all. The balance equation in part A should be including energy. Consider what happened to the color when the tube was released. Reaction is exothermic. It's endothermic. We figured that out. What gas was predominantly present at low temperatures? At low temperatures is N2O4. No, at low temperatures, that would be, N2O4. So that's when it's colorless. And the what gas is predominantly present at high temperatures? Well, NO2, because it's dark brown. How would you describe the chemical composition of tube when it was at room temperature? It would be, we would consider it at equilibrium at room temperature, so the rates have stabilized. If one tube was filled with NO2 and another tube is pure, okay, careful with this one. If one tube were filled with pure NO2 and another tube with pure N2O4, what might be true of the colors you would expect to see if the tubes, after they sit for a minute at the same temperature? What evidence do you have that your prediction would occur? What do you think is going to happen? You're starting with pure NO2 and pure N2O4. Mr. Preeb, what was going to happen?
They should both return to the equilibrium of room temperature.
Yes, because if you're talking about the pure N2O4, what you should expect to occur, you should expect it to go in this direction. It can start like that, and there could be nothing here, but some will go this way, and vice versa. You'll just start with pure NO2, and some of it will go return to N2O4. And you're quite right; they'll both be the same color at room temperature. Yes.
So let me ask you a question. Is the volume of the gas on the left and the volume of the gas on the right equal in this sense?
I think they said identical tubes, so I'm going to assume so. But you can the only thing that'll be different if they're non-identical tubes was the actual volume. So you may get one may look slightly darker than the other just because you're looking through more gas. But if you were to put both of them in the freezer, both would be clear. You look right through them equally. There's lots of videos online, just situations such as our own, where they actually have two glass containers of this containing the system, and they just alternate it back and forth. They can see it change, and it's a bit of time-lapse photography though, because it doesn't happen right away. It takes a little bit of time for it to work. Okay, good. Any questions after that? Yeah.
How do you get your N2O4 or pure N2O4? And then you say that the reaction is happening at an
How would that actually occur? Probably you'd have to react two other chemicals together to make one or the other. Okay. For example, if you take nitric acid and copper, you'll produce pure NO2. Okay. It's noxious gas, but almost from the moment you form it, you'd have to have it somehow in some sort of other pressurized system or something, or at a high enough temperature that it won't go back. So yeah, you'd have to somehow isolate them. One at a cold, one at a hot. I don't know. Yeah, that's a good question. Very, very intuitive. They're very good. Okay. So conclusion. Our conclusions to the exercise 2. Number 1, temperature affects equilibrium. Two, new temperature leads to a new equilibrium point. Number 3, and this is a little less obvious, equilibrium, excuse me, equilibrium does not depend on the concentration. Does not depend on the concentration of either the product or reactant. At the start. And at equilibrium, equilibrium there is no macroscopic change, And by macroscopic, what we mean is visible.
Is it at equilibrium start or at equilibrium?
At the start of the reaction. Oh, I'm just from previous. Okay, so there's no visible change. However, and this is, you didn't get this from the exercise, Rudy, because you couldn't see this, but just as a point of fact, that there is, or there remains, microscopic change. Okay, so molecules are reacting, they're changing all the time. It's just that there's, because at equilibrium there's they go equally both directions, you won't notice it. Dynamic equilibrium. Continue on page 2. Wait a minute. Oh, page 2 is over here. I forgot, I didn't use my... And this is the idea of dynamic equilibrium, is the microscopic ones. Dynamic, what did I say here? Equilibrium. So dynamic equilibrium. Thank you. So dynamic equilibrium means dynamic means action, okay? Where we get dynamo or dynamite, there's action involved. So the action is on a microscopic. And equilibrium, as it suggests, is like a teeter-totter. Okay? Just like a teeter-totter, it's at equilibrium. Overall, you don't see any change one way or the other, even though there is stuff going on. So here is a diagram of, this actually is showing the reaction that we talked about in Hebden and in this example. We've got N2O4 and NO2. So you see that this guy here, you can't see that. So this guy here is the N2O4, 2 N's in the middle, 4 oxygens, and the N and the 2 oxygens on these guys, okay? So exothermic and where's my room? This is just kind of like a little, don't feel that you have to do what I'm doing here. I just do it because it's helpful to me. Fortunately, I don't have any really nice NO2 looking highlighters. So I'm going to just have to pretend that orange approximates the issue. So in this case here, NO2 is warm, and so when it goes this way, it's going to let go of its energy and become NO2. So really and truly, if you were to look at the different systems, you would get way down here, and this would be at the very, very cold. It would be pretty well all N2O4. But as you heat it up, as you increase temperature, so increase temperature, as you increase temperature, it gets darker and darker and darker until it's almost 100% NO2. Almost. But at any point along this continuum, there are still individual atoms, or molecules, being transferred back and forth. The question is how much, at what rate. Okay? So if I stop the temperature right here, right in the middle, this would approximate what do we call that, room temperature. Okay? So that's dynamic equilibrium. There is another type of equilibrium, as aforementioned, and that is what we call static equilibrium. And static equilibrium is when no change will occur, either macro or micro, unless the system is somehow pushed. And we're going to talk a lot about that. Okay, we good?
What do you mean by like push? Kinetic energy then?
Temperature, yeah. Thermal energy is one way, but there's other ways of doing it as well. When we talk about Le Chatelier's principle, you'll see that it can be pushed by concentration or removal of reactants, removal of products, pressure, lots of things.
Push, are you suggesting motion, or more like
Change in the environment,
yeah?
change in reaction conditions could make it go one way or the other. Okay? Oh, yeah.
Like during the trends, they hold it during situation, like there's microscopic exchange.
Yep.
Where is that activation energy? You're not
Both will be reaching, like from both sides, they will be reaching their activation energy. Either way, from either side. But the rate is equal. In some situations, like some reactions require an addition of a lot of energy because they've got a very high energy hill to climb. Okay. Some reaction mechanisms, all the energy they need is the vibration of the atom or the molecules in the system. Those ones are they tend to go almost right away, okay? And they'll go back and forth too. It also depends on the relative height of the activation energy in the forward and in the reverse. If they're somewhat similar, then they'll go back and forth quite readily. Okay, if it's really big, not so much. Yes, sir.
For the diagram above, the NO2 to N2O4.
Yeah.
Is that a high temperature on the left or a low temperature on the left?
A high temperature. It goes to NO2. It goes this way.
So high temperature on the left or low temperature on the left?
No, as you increase temperature, it goes from N2O4 to NO2. NO2 is the dark brown gas. This is dark brown. Okay? So at low temperatures, if this low temperature is here, it's going to be predominantly N2O4. As I add heat, it gets warmer and warmer and warmer, and more of the N2O4 becomes NO2. Yeah, this is probably you should make sure that you have this little thing in here. As you go across, you have an increase in temperature going this way.
Okay, so it's not as you go up or left, the temperature increases?
No, it's going across this way. This is not a graph, okay? This isn't a graph. This is just a little visual showing that in the system, like the area inside this rectangle are all the molecules that are present. Okay? So well, that's not really true. If at any point along here, these are the relative proportions of the two different kinds of molecules. So down here, at very low temperatures, it's pretty much 100% N2O4. Okay? But as I increase the temperature, now I go here to here, so I've increased the temperature. Now it's about maybe 1/3 NO2 and 2/3 N2O4. If I continue to add energy to it, I bring it up this end of things, then it's very small amount of N2O4 and mostly NO2. But at any point along here, there still is the concept of dynamic equilibrium. There still are molecules going both directions. Yes?
So to translate the symbols at the bottom,
Yeah.
it would be as the graph, or as you progress left, the temperature increases.
Yeah.
And what's that little squiggle infinity?
Say again.
It's E then a little squiggle or something.
Temperature degrees.
Okay.
This is increased. This is an up arrow, increasing the temperature, okay, as you go this way. Okay? Now what color did we use on that first page? I don't even remember anymore. What did I do with it? Oh. So it was pink. Are we good? So we are now reactants. Double-headed arrow like that means this is, goes in both directions, which means that this is an equilibrium reaction. Goes to products. This is a little bit misleading for some students. This double-headed arrow is somewhat misleading because it's sometimes interpreted as that these are equal. They're equal. How do I say this? The implication is that in a situation like this, the concentrations are 50-50. Okay? That's not true. It's almost never 50-50. Okay? So, just as a little, the reaction can go strongly over this way. It can go strongly over this way. But there will be some point where products and reactants are in this ongoing exchange. And it is never concentration of reactants to products. Never. It'll be way one way, way the other way. Sometimes it's close to the middle, but not 50-50. Okay? So in a reversible reaction, there are forward and reverse rates of reaction. These are usually different. Okay? Okay. Rate of reaction increases as the concentration of reactants increases. Okay, so we've done this, I think we did this in Chemistry 11, but from here on, if you see this, square brackets means concentration of something. So if you see, if you see square brackets means concentration of something. So if you see something like this, reactants, that just means the concentration of reactants. And conversely, concentration of products.
How will we know the difference between if it's a number in there? How will we know?
Oh, don't worry about it. You'll know. You'll know. We're going to start talking about that a lot right now. Okay, we talk about rates of reaction in this way. The rate, the rate, I'm going to put a small f here. So this means the forward rate of reaction is equal to, K means a constant. Have you guys done that in physics or anything else before? K is a constant? Okay. So K, F for the forward, times the concentration of the reactants. Yeah.
Is it essential that we use a star?
No.
If we need to
You can use a dot if you like. You can use an X if you like, but I find X's start to get, I get confused with them. I'm easily confused though. Say again?
K plus and T, we're working on the T equation.
Okay? So, what this means is just that the reaction rate is equal to a constant times concentration of the reactants. And the reverse is true too, such that the reverse rate, so reverse rate is equal to another constant, it's a different constant, times the concentration. Huh?
So, do we need to know these formulas for the test? And if so,
Oh, you'll be using these. This is not a question of knowing. You're going to be using this. KEQ is what we're going to talk about right now.
yes, so
This is going to be pretty much the rest of the. That's not true. A lot of what we do now in this chapter is going to be calculations using KEQ.
So are we going to get a little cue card like the previous use, like for every chapter 11? Have a little formula card? That looks pretty good.
If you like. Basically, it's just this. So I'll spare you the ink. It's KEQ. This is called the equilibrium constant. Is equal to the ratio of the product concentration divided by the reactant concentration.
We should find a short way to write equilibrium. Oh, that's the equation.
Yeah.
Incorporate equilibrium.
So if you have, let's just say for ballpark, let's say you get one of those really rare situations where there is a 50-50 concentration. Let's say it's an even up concentration, okay? So if that is true, so I'm just going to go over here. If you had a 50-50 system, then KEQ will equal, say, 50 divided by 50 is equal to 1. So the KEQ for that system would be 1. Okay? And the reality is, a good way of thinking about KEQ is that
What's the unit of
it is dimensionless. It's a dimensionless number. Yeah. Yeah. KEQ is a measure of how far forward a reaction proceeds. So if you look at this, just hang on, I just want to get through this thought, but I'll take a question. If the concentration of the products was very large, and concentration of the reactants was very small, what would be KEQ? Would it be a large number or a small number? Let me say it again.
Large number.
It's going to be a large number. Let me, because some of them are still writing. If the concentration, I want you to think about the words that I'm saying too, okay? If the concentration of products was very large and the concentration of the reactants was very small, what type or what magnitude would the value of KEQ be?
Pretty sizable value.
It's going to be large, okay? That's what I mean when I say that KEQ is a measure of how far forward a reaction proceeds. So, you should expect to experience KEQ values in the realm of 10 to the minus something. You should also expect to find KEQ values to the magnitude of K to some plus value, 10 to the some plus value. Some plus value means that this is very large. It goes way, way, way towards completion, but it doesn't get there because it's equilibrium. If it's very small, that means it hardly moved at all, but it's still in equilibrium. Yes, Mr. Creed.
So will you get a different KEQ whether your reaction rates forward or backwards, or will you use the same KEQ?
You should get the same KEQ value for a certain system, but it changes by system.
The same system forwards and backwards, we will use the same constant?
I'm not sure I understand what you're saying.
Above the KEQ equation, you have rate R is equal to KR times product. What are we putting KEQ in for our KR?
It's going to be, I'm not sure quite how that works. That's for the reverse, yeah. I think Hebden goes through a little bit of mathematical juggling to show you where it comes from. I don't bother going there because, number one, I don't think it's relevant for what we're trying to do. It's extra brain taxing, and I don't think we need it. He likes to cross all his T's and dot all his I's, though, so that's why he does things like that. Yeah.
So will we need the previous Q reaction rate?
No, this is KEQ. Just wait till we start doing some calculations, and then it'll be, oh, okay, that's what this is about.
So we don't need the rate.
I wouldn't worry about it at this point. No. Okay. So you can see at the bottom of the page we have additional points to make. So at equilibrium, the rate of reactant consumption is equal to the rate of product formation. Second point, the concentration of the reactants does not equal the concentration of the products, or at least rarely. And to be honest with you, I don't think you will ever, no, that's a lie. I think maybe once you run into a situation where the products and reactant concentrations are the same, so but I think by and large you'll never see it in the calculation. Okay? And at equilibrium, the concentration of the reactants and the concentration of the products does not change. And the forward reaction rate and the reverse reaction rate do not change. So rate F and rate R do not change. And the last statement that I'm going to put highlighter in there and let it dry so I don't smear everywhere.
Would the semicolon represent when it says reactant semicolon product does not change?
Say again. Where are you? Where are you?
The semicolon, what is that?
Reactants, the products does not change.
So what's the semicolon?
Just a separator, that's all.
Oh, it says, oh, okay, cool.
Yeah, neither of them change.
I was wondering about like a ratio or something.
No, no. And a system not at equilibrium will spontaneously move towards equilibrium. Thank you. Spontaneously move toward equilibrium.
Why is that one highlighted? Is that the most?
Because that's going to be really key. It's sort of like the last statement in the kinetic molecular theory. Everything's leading up to this one. Okay, where did I put that? Is it here? Oh, here we go. Okay, I'm gonna show you something, and this may take us pretty close to the break. If it does, then we will break and come back. But let's on page 40. On page 40 of Hebden, we have this system. Got a funny feeling I need to get some white paper. No. This is something that is assigned, but I don't know if I'm going to actually make you do it or not. Okay. This is on page 40. If you turn to page 40 of your of Hebden, please turn to page 40 because I need to take this out of the way because I need to show you this on a graph. Okay, so grab Hebden. Find page 40, and you'll see that this is talking about just a really simple situation that's a theoretical entity where you start with this is the concentration. So in other words, there's no B present in the beginning. 0.00 molar, nothing. That's concentration, right? Concentration is a molarity. Okay. But you're starting with 1.200 molar of whatever A is, okay? Now, this is given that the forward rate of reaction is 0.500, 0.50, so it's a dimensionless number. The reverse is 0.1. Now what you're asked to do in this thing is, first of all, you're asked to plot this on a graph. Okay? Now I'm going to show you what the graph looks like. Well, I'm going to have to pull out, it's way too close. Okay, so that light, I wonder if I can get, there you go, that's better. Okay, so this is what it looks like, where I've got A in green and the B is in blue. So if you look here, you can see that at 1.200 molar, time 0, we're at 1.200 molar of A, and we're at 0 molar of B. Now we let the clock run. And if you were to plot this, what you'd see is that at 1 minute, the concentration of A and concentration of B is the same, 0.600 molar. And as time goes on, more and more A is used up, but it flattens out right here. Okay? At the same time, you get more and more B until it flattens out. In other words, when you're here, at this place here, this is where equilibrium has occurred, is where it's level now. This is moving towards equilibrium, this is at equilibrium. And at equilibrium, if you want to solve for the KEQ, what is the equilibrium constant of this situation, you'd have to look and say, well, what is the concentration of the products divided by the concentration of the reactants? Well, the concentration of the products is 1.000 molar. The concentration of the of the reactants is now at 0.200. So I divide 1.00 molar by 0.2. KEQ for this system is 5. Okay? Now, if you go on to the next page, 7, it says, okay, what would happen if at 11 minutes, we change the concentration? There's a concentration at 11 minutes, but what would happen, where is it, 11, if I injected some, what am I throwing in there? I'm throwing in some B, okay? What would happen? It says, now let's see what happens if the previous equilibrium is upset by adding an extra 0.6 molar of B at the 11th minute. So as to increase B from 1 molar to 1.6 molar. Okay? So this was at 1, now it's up to 0.6. So if I graph that, and I graph the rest of this, check this out. I'm going to need more paper. So here we are. I know the little black lines are a little bit much. But so this is where we got to. We got to equilibrium here, and we're at the 10th minute. And so at the 11th minute, we inject, so we're increasing the concentration instantaneously of this to 1.6. and then to see what happens. So what's going to happen is the addition, some of the addition is going to be used up. It's going to be continually used up. Oops. It's going to continue to be used up until it falls back to an equilibrium point. Okay? On the bottom end, down here, it was at equilibrium, but because you added more of the B, more was converted back to A. So if you check this out, watch what's happening here. It increases, and then it goes to equilibrium as well. So here and here, we are at equilibrium again. Now this is where it gets a little bit interesting. If you look at the values at equilibrium, it's 1.500 molar at equilibrium of the product, and the reactant is 0.300 molar. KEQ has not changed. It has reestablished at 5. So what's this telling me? That this system, the KEQ for this system, is 5. It doesn't matter who you are, it's going to reestablish at 5. It doesn't matter what you do to it, it's going to reestablish at 5. With the one possible exception of temperature. Temperature changes things. But when you're talking about concentration differences, it will reestablish at 5. And all of our calculations involving KEQ are concentrations, in fact. Okay? Yes, sir.
So just to confirm, you made this graph by taking the concentration by time?
Yeah.
Okay, so the rate has nothing to do with it?
No, the point of this, the point of the exercise is to demonstrate that when we're talking about KEQ, K for one thing is a constant. Okay, it's an equilibrium constant for a particular system. In this case, this system you're just calling it AB. You're gonna run into all sorts of systems where you're going to be calculating the actual KEQ values, and you're going to be concentrating, knowing the KEQ values. You're going to be concentrating around calculating the concentrations. So this is a tool by which you can play. You can use it to play chemist with, basically, predicting the different concentrations and all that. Okay. Okay, it's close enough. Let's take a break. Give you 10 minutes. Yeah. Okay, so hey dear.
So I want to check that we're missing the such tiny radius.
Something? Oh,
The
just a minute.